Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I welcome you all into my today lecture. Our today lecture is lecture number 32, and these are the almost the last part of the unit number 15. In our today lecture, we will study the RLC series circuit. So let us start with the name of Allah Almighty. Before this, in the previous lecture, we have studied the series circuit, the RL series circuit. Today, we are going to study the RLC series circuit. The RLC circuit is very useful and an important circuit because the RLC circuit is used in the AM FM radio tuner. So this is the used in what? Used in the FM frequency modulation, AM the amplitude modulation, radio tuner circuits. In the uh, radio tuner circuits, right? This is one of the important that the tuning circuits are those circuit which select the desired frequency and reject the unwanted. For example, if there are many channels on your radio or in your television, you only watch sports, so your tuning circuit will select the sports channel for you and will reject the unwanted. Similarly, this is good to maintain the good voltage in long and medium distance power transmission. So such kind of circuits are used for the power transmission over a longer or a medium distance power transmission. So such circuits can be used for the power transmission also. So they can be used to transmit power. Similarly, they are used in transformer to avoid sudden faults currents. So this is why it is very important to study such kind of circuits. Here you see the RLC series circuit. So if you look across this RLC circuit, here the AC source or the VRMS source is here, the AC source. This is the sinusoidal current that flows in the circuit. And here you see that this is the V instantaneous. I would like to write. And here we have this as the voltage drop across the resistor. And here the power dissipation is in the form of heat energy. And here you see that there will be the VL as you see. So this is the potential drop across the inductor. And here you see the capacitor, and there is the VC, the potential drop across the capacitor is the VC. Now, the most important point is that if you just look, there is the same amount of current passing through each of the electrical component. Why? Because there is only one path for the flow of current. So here, if we just look to the phasor diagram, if you remember that I told you that since from our previous lecture, I told you that in the pure capacitive circuit, in the pure capacitive circuit, in the pure capacitive circuit, I leads, the current leads the voltage, the current leads V, the VR, right? The VC leads by pi by 2. So if you remember, then I draw the diagram to you, and that is indicated by this portion of the graph here. So if you just look to the phasor diagram here, that is the here we have the phasor diagram. Here you see this is the phasor diagram diagram for the RLC circuit. Here in this phasor diagram, you see we have one the V phasor and we have one the Z phasor also in term of resistance and in term of the potential difference. Now you look that if you see that in this part of the graph where you see look that I leads what I leads VC with pi by 2. Here you see this one. So this is happening in this part of the circuit, okay, like here this is the VC, okay, and here this is the capacitor, and across the capacitor we have this the VC. Across the inductor we have this the VL, as I already labeled in the previous diagram. This is the inductor, and here the resistor, and the IR drop across the resistor you already know that could be the VR if this is the resistance. Now for the second part, look, if you just compare the RL series circuit, for the RL series circuit, the R that is the RL series circuit. In the RL series circuit, the pure induct, that is the voltage across, in the pure inductive circuit, the voltage across the conductor leads the current by pi by lead the current leads I by pi by 2. So it is this part of the circuit. If you see, look here as you see it. So now look, uh, in order to draw the complete phasor diagram here, look what is going to happen if I just show you write this diagram, then it will look like this. For example, you see here shapes, and which shape I should select like this. See here, look, if you just see that in this diagram, look here, that if we have the if we have this will be if you see in this diagram, look, if we have this as the V, right, the V phasor, the VL, and if you see that here we have the VC phasor, and the VC phasor I will denote by this is the VC. So what will be the resultant for this? This is the VC. Now if the VL is greater than the VC, or just apply the vector algebra to the diagram here. Here we have this is the VR. Then what I can write here, they definitely look the resultant sum of these two vector, the resultant sum of these two will be what? It will be the VL minus the VC, and let's say that I choose it in a direction like this one, okay, to complete my phasor diagram, right? So this will be what? This will be the VL minus the VC, and let's say it is like this. Okay, now you see that this is the resultant VRMS here is this one. This is the total voltage potential difference applied V. Usually I write it as the VRMS. Even if it is not in your book, write the term VRMS. Then I told you that in the circuit only VRMS values, in the voltmeter or the meter measure the VRMS. So this is why I'll be writing here the IRMS for my convenience, the IRMS and the VRMS. So it is that VRMS with us, and this is the angle phase angle I. So we now wish to find this, okay, and the total impedance of the circuit, the resultant impedance of the circuit. So if you look into this diagram here, the VRMS is equal the VRMS, and this VRMS equals to the it will be equal to the VR, the VR square plus the VL minus the VC whole square, and it is just say this under the root R. I can write that the VRMS equals into like this will be the IRMS square into R square, and here the IRMS square I will take common, and this will be the XL, the inductive reactance, minus the capacitive reactance, and then I will make it like this. So this is very easy also, that if we apply the Z phasor circumstances like here, then it will be very simple. What I'll be writing, that the total Z is equal to R square in the easiest way into XL minus XC whole square under the root. So just in one line explanation. Here now what is going to happen, this IRMS square is common. I will take it common. The IRMS square and its square root will be just IRMS, and I will transfer the IRMS on the left side, IRMS, and the equation will look like is R square plus the plus the XL minus the XC whole square, and this is the impedance of the circuit. The ratio of VRMS to IRMS is the total impedance of the circuit, the combined resistance of the resistances and the reactances, and it will be R square plus XL minus XC whole square under the root, like this one. So now here you see that, look, that if you have the resistance in a circuit, the the RL circuit, and if you just put there the capacitor, then the impedance decreases. Why? Because here they have the opposing effect from each other, right? So we have one on this. The next important point here is the next important point here is the phase angle for the base. So this is the combined or the total reactances in the circuit, and for the phase difference, for the phase angle, look for the phase I. What we can do here is that it can be written as like the tan. Here I should write the tan and inverse or the tan pi will be equal the right. I should do it like this. That is that this angle will be equal to, if you just look at to this diagram, that is the this one and this one, like that. But better to now use the phasor diagram, the Z phasor, it will be more good. So this one, and this is the Z, the total impedance, and here I have this the XL minus the XC, and here I have this as the R. So this will be equal to the tangent inverse of XL minus XC by R. And this is how we can find the phase angle, right? And the source, that is the, so if the current is represented by the cosine function, right, then we can write it like this, that the current in the circuit will be just very simple, Im into cos omega t, and in term of this phase angle, it will now become Im, the total current that flows in the circuit will be omega t into plus pi. And similarly, for the uh, power consumption or for the power of the circuit, power in RLC circuit. So for the power, what I will write here is the same equation, that P equals I into V IRMS into VRMS. This is RMS values. Okay, into cos of pi, and I already called you, I already told you that this is the power factor. Okay, the power factor. Clear? This is our power factor. Now you know that here for there are many cases that, as you see, the z equals that the r square plus xl minus xc whole square under the root. So if this term lock now there are cases, and what are those cases? The case one, if xl is greater than xc, then what will happen? When they rather better to write, for example, if the term xl minus xc, if it is positive, then xl will be greater than xc, and the phase angle is positive, and the circuit will be acting like an inductive circuit. In other ways, I can say that the circuit that is the circuit, the current I will lag behind the applied voltage by pi. This is one. The second important point here, that if XL minus XC, if it is negative, right? If it is negative, less than 0, then what will happen? That XL will be less than XC, and in this case the phase angle pi will be negative, and the circuit will be what? A pure capacitor. This is pure capacitor circuit, and this is pure what? And this is pure inductive circuit, pure inductive circuit. Now that is the in this situation, the current will leads the voltage by pi by 2. Now there is another important case, the third case, and we see that what, that if xl minus xc is equal to 0, and then what happens if xl is equal to xc, and in this term, what will happen, that z will become what? R square, or it will become R, and the circuit will be what? The circuit will be purely resistive circuit, and in this case maximum power will be transferred, power will be maximum power will be transferred, right? That is why, because what is the reason? The circuit has minimum z. The circuit has what? Minimum impedance. The circuit has the minimum impedance or resistance, the minimum impedance or z or resistance. Okay, in this case that is the situation where we can call this as the resonance in RLC series circuit, and the circuit is said to be in pure resonance. In this case, the circuit is said to be in resonance, is said to be in resonance, and maximum power will be delivered. Maximum power will be delivered, right? In this case, I will be what? I will be maximum. Current will be maximum. Why? Because the impedance is minimum. Now when this thing will happen, what does this means? That XL equals XC. Alright, let me choose this graph. Later on I will be explaining this to you here. Okay, now what does this means here? That look, we know this is omega L, and we know that this is what, that this is the 1 over omega C. So omega square will be equal to 1 over LC, and you know omega is equal to 2 pi f whole square, and it will be 1 over LC. Or I can write it like this, that this f will be equal to 1 over LC square root into 1 over 2 pi. This frequency is called the resonating frequency, or the that is the frequency. It is this frequency, this one. Okay, here you see that you have the current, what, here you have the current maximum, right? Why? Because you have at this point the current is minimum. Right now look, if this frequency, it is this frequency 1 over 2 pi ln to c under the root. Okay, 1 over c into L under the root. Clear? So we have one, the for this is known as the resonating uh, frequency. Okay, and here you see that the circuit has, look, at one end of the resonating frequency the circuit has inductive effect, and at the other end it has what, the capacitive effect, right, for this FR. And when the inductive reactance becomes equal to the capacitive reactance, the circuit will purely act an inductive, and maximum power will be transferred, right? So this is the known as the resonance and the RLC circuit. Now the next topic is the principle of the metal detector. This is very easy. It works on the principle of this phenomena of the induction, mutual induction, and the phenomena of beaten waves, and that is very easy, and I leave it for you as an assignment, and you study it yourself and discuss with me. However, I will explain to you the maximum power transfer. Maximum power transfer. Maximum power transfer. Right? And the maximum power transfer, or it is sometimes called the maximum power transfer theorem. Okay. Now here for the maximum power transfer theorem, here I would like to tell you that the electrical energy from supply is delivered to the load, where it is converted into a useful work done. Right? That what here we want to study, that electrical energy, the maximum electrical energy from the source or from the supply, from the source is delivered. Our main point is to deliver it to the load, resistance, to the load, where it is converted, into a useful work done, Okay, but this is not always the case. The power, the entire power cannot be converted into a useful work done. It is not available to us because of the heating effect. So this is impossible. The entire power input impossible due to the heating effect. The heating effect, that is that some of the power must be dissipated in the I square R form. So this is impossible that we can convert the entire useful input into the output. But we have learned that the load size affect the power transfer from the supply source, right? This is what you have learned in the chapter number 2, where we have studied the maximum power output. The maximum power transfer theorem ensure the condition to maximum transfer power, right? Yeah, to that is the MPTT ensure the maximum power transfer. And this maximum power transfer, this theorem, it states that maximum power is delivered to the load, for example by the AC generator, to the load when the load resistance RL becomes equal R, where this R is the internal resistance of the source. Internal resistance of the source, right? And this graph, it would look like this, that if you just plot the power against the load, then the graph obtained look like this. It is like this. Okay, and here you see that if you just see, look, this is the maximum the maximum power line. Okay, here, and you see that it is at a certain resistance, that is a load resistance, like this one. And this only possible when the load resistance becomes equal to the internal resistance of the source, right? So this is the total impedance for the AC circuit. This is what I will be writing Z. Okay, because we have not R, we have the Z. And this for the load, and it will be equal to the Z of the ZG, that is the ZG means the impedance of the generator output. Generator output impedance. Output impedance. Okay, and here you see that, look, when the load resistance is 0, right? If you just see, look at this point, if the load resistance is 0, what does this mean? That if the internal resistance of the battery is 0, no power is transferred. Why? Because you just see, look, what is here for R is equal to 0, no power transfer, right? Why? Because there will be no voltage source across or potential drop across the RL. But here, if it increases, look, if you just see, look, if the load resistance increases, then a stage will reach that what will happen? The power transfer will again become 0. Why? Because if the load resistance is infinite, then it will limit the current to 0. And if the current is limited to 0, power is equal to what? I square R. And then there will be no power delivered. So this is our today lecture, and inshallah in the next lecture I will explain to you the Maxwell equation, and that will be the last topic. Okay, so inshallah see you in the next lecture.